Alright, in this unit we're going to be getting into kind of a basic intro to chemistry as far as its relationship to biology, which will be a nice lead-in to our next topic, which is going to be getting into these biomolecules, these macromolecules, and kind of the chemistry behind them and how they function in life processes. So we're just going to be focusing on just some basic chemistry stuff and how it relates to biology. So just starting from the beginning, get some terminology out of the way. We're going to start small and go bigger. We know atom, smallest unit of matter. It's the smallest unit of matter that can't be broken down any further. There are individual parts of an atom, but as far as a small unit of matter, it's going to be the atom. We know the inside, the guts of the atom. It's got protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. They make up most of the mass of the atom. Protons have a positive charge, neutrons are neutral, so the inner core of the atom is going to be have a positive charge. The electrons that surround that atom are going to have a negative charge. They don't have hardly any weight. The weight is insubstantial when it comes to the overall mass of that particular atom. So when you're looking at elements, say for example carbon, or phosphorus, or hydrogen, or helium, you're looking at an element. Most of the mass of that particular element that's made of those atoms is going to come from the protons inside the nucleus of that element. So atom's the smallest unit. We know you can put a bunch of atoms of a particular substance together and it makes up an element. So all the atoms of one particular substance go into form an element. So for example, the element gold. Alright, gold is made up of a lot of small atoms of gold that make that element gold. Same thing with carbon, helium, and other elements on the periodic table. You can take elements, and you can take elements of the same type. You can take elements that are different. You can combine them or bond them together, and you can make a smallest unit of a compound, which is a molecule. You can take, for example, a carbon element, and you can bond it to another carbon element, and you can make a molecule. You can bond carbon elements with oxygen elements, and you make molecules. So your molecules, 2 oxygen atoms, 2 carbon atoms, right? The smallest functioning units of a compound, and you stick those with a bunch of other types of elements, maybe multiples, and you get a compound. So these are the interchanging words: atoms, smallest unit, elements made up of those atoms, molecule made up of a bunch of elements, and then compounds made up of a bunch of molecules. So my examples here: NaCl, sodium and chlorine; CO2, 2 oxygens and a carbon; C6H12O6, formula that you're going to need to know very well for biology, made up of carbon, hydrogen, and oxygen. Although there are about 25 common elements found in biomolecules, there are only 6 of them that are really, really common. 6 of them that you need to be familiar with. So let's look at these 6 more common elements. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the major common elements out of all that I've listed before. They're going to be most common in the biological makeup of processes and those macromolecules we'll be getting to. Carbon probably being one of the biggest ones. That's why it's on the top of the list. Not necessarily the most important, though. Alright, so we know what atoms are. We know elements. We know that hierarchy building. Let's look at bonds. Let's look at how we hold this stuff together. The way it works is you have an element, and in that element you have the nucleus, and then on the outside of the nucleus you have electrons. Each element has different levels or layers that these electrons can fit into, and we call them clouds or levels. And most of those levels, or most of those electron clouds that surround the nucleus of an atom, can hold up to approximately 8, for the most part, electrons, and so that gives the potential to interact with up to 4 different atoms, atom to atom, or make 4 different bonds, depending on the number of electrons that are in that outer shell or outer cloud. Atoms are going to want to, or molecules are going, or just say atoms. Atoms are going to want to have a full set, so they're going to want to strive for 8 in that outer shell to balance out, maintain equilibrium, those types of things. So they're always looking to bond to make themselves more stable and reach that homeostasis, or that equilibrium. So, for example, you have these 2 oxygen and 2 hydrogen. Hydrogen is going to have one electron in its outer energy level, whereas this oxygen, okay, if you look at this oxygen's outer energy level, it's going to have 6. So for this oxygen to become stable, it's going to want to fill its outer energy level, so it's going to need 2 more electrons to make 8. This hydrogen only has 1, so to make it stable, it wants to get rid of this 1 so it has a complete outer energy level, in essence. So the easiest way for nature to make this happen is you get 1 oxygen and 2 hydrogens. The 2 hydrogens will give up these electrons. It'll fill up this outer energy level. You get 2 bonds occurring, one between these 2 atoms and one between these 2 atoms, and you get, in essence, a water molecule as a result. When water forms, looking at water, water is a fundamental substance when it comes to biological processes and to life. It has some very unique characteristics that make water one of these fundamental substances. It has a property called cohesion. It is very adhesive. It is considered a universal solvent, and it has the ability to expand. And we'll look at these characteristics as we move on throughout the year. But in essence, water's cohesive properties, it gives it ability to stick together. Okay, water molecules can stick together. It forms something called surface tension. If you ever look at the top of water, whether it be in a swimming pool or a lake or a glass that you're drinking out of, you can see a nice smooth surface, and it's due to those cohesive properties. Water's adhesive properties allows it to stick to other things. So it can stick to windows and cars. It has that ability to adhere to other substances. And water's considered polar, or its molecules considered polar, because it'll have a slightly negative and positive charge on either end, kind of like a magnet, or a little bit like a magnet. And so this property allows water to be a very good solvent, which it gives it the property of physically breaking things down or dissolving them when they're submerged in water. All right, pH. pH is also important when you're looking at the biology and life processes. So a quick review on pH. We know we have the pH scale. It goes from 0 to 14. Depending on where a substance falls on the pH scale, it can either be an acid or a base. Acids are usually between 0 and roughly 6.5, 6.7. Okay, we know something is going to be considered neutral, so it's not an acid, nor is it a base if it falls between that 6.5 to 8.5, or excuse me, to 7.5. And then a base is going to be on the upper portion of that scale. So anything from roughly 8.5 to 14 is going to be considered a base. Looking at the pH scale, the lower the number, the more acidic something is. The higher the number, the more basic it is. So if you have a substance that is measuring a 1 or a 0, that is a very strong acid, cause more problems than, say, something that is a 5 or 6, which means that it would be a weak acid. Same thing or same concept for bases as well.